Modeling with quadratic functions. Our objective for this lesson is to write equations of quadratic functions using vertices, points, and x-intercepts, and write quadratic equations to model data sets. Okay. So in our previous lesson so far with quadratics, they've always started by giving us an equation, and from that equation we determine its vertex, where it's minimum, maximum, what the graph looks like, whether it's increasing, decreasing, so forth and so on, axis of symmetry, focus, directrix, all of those things. But they always start by giving us the equation. Okay, today we're going to flip it around, and we're going to start by them giving us information. We know information about the quadratic. We need to find the equation. Okay, so we're going to be actually writing those quadratic equations today. Okay, depending on what they give you, we'll use different forms of the quadratic, of a quadratic equation. But we had vertex form, standard form, and we even had an intercept form that we didn't do much with. But we'll go back and look at those because depending on what information we know, one of those will be more useful than the other. Okay, so first of all, if we know a point and its vertex, okay, then since we know the vertex, the easiest way would be to use vertex form. So that would be using y equals ax minus h squared plus k. Okay. So if we know the vertex, we're going to use here vertex form. Okay, and we're going to walk through an example on doing that. Okay, if we know a point and the x-intercepts. Okay, this is where that intercept form is going to come in handy that we didn't do a whole lot with in the last sections. We're going to do some stuff with it this section. So we would take a, and then it would be x minus p, again where p there is one of my intercepts, and x minus q, where again q is the other intercept. Okay, and if we're given 3 points, here, all bets are off, and we actually solve a system of equations. Solve a system of equations. But you end up using the standard form here. You use y equals ax squared plus bx plus c. So we use the standard form, but we'll need to use it in a system of equations, and we'll do an example of that one also. Okay, so here for an example 1, here we have a graph, and this graph shows the parabolic path of a performer who is shot out of a cannon, where y here is the height in feet, so this is how high she goes, and x is the horizontal distance traveled, this is how far over she goes, okay, in feet. Write an equation of the parabola. The performer lands in a net 90 feet from the cannon. What is the height of the net? Okay, so my net is over here. Okay, first things first, write an equation of the parabola. So let's do that first. Write an equation of the parabola. So if we notice on this, we are given here a point, 0, 15. And we're also given here her vertex. So we know a point. Let's write down what we know. We know a point of 0, 15, and we know our vertex is 50, 35, because we can tell that's our highest point there. Okay, so there's my h and my k. So since I know a point and the vertex, I'm going to use here this vertex form. So we're going to use y, I'm going to write it down first, y equals a x minus h squared plus k. All right, so let's plug in what we know. First of all, we know my h and my k. So we'd have y equals a x minus 50 squared plus 35. So really, I have my equation all out except my a. I need to find a. So to find a, I'm going to plug in an x and a y that I know. So I'm going to plug in x and y to find a. So I have an x and a y. This is just one of the many x's and y's that will work. Do you agree there's going to be many x's and y's? Every single point on this graph is going to be an x and a y that will work in this, but we know one for sure, when x is 0 and y is 15. So we're going to plug that in. So we'll have 15 equals a. Now my x is 0 plus 35. So now if you notice, now I have an equation with all numbers except for my a. So now we can dot, dot, dot solve for a. So let's do that. So we have 15 equals a times negative 50 squared plus 35. Okay, let's get our calculator out and take negative 50 and square it. And we get 2,500, so we'll have 15 equals. Okay, let's subtract the 35 from both sides. So we'd have what? 15 minus 35. Well, here, we'll just 15 minus 35. Make sure we don't make a mistake. Negative 20. Divide both sides by the 2,500. And my a equals, again, no decimals, we want exact. Negative 20 divided by 2,500 is that. Math, enter. Negative 1 over 125. So that's my a. So now that I know my a, I can write my equation. So y equals a, negative 1 over 125, x minus 50 squared plus 35. So there's the equation that will graph this parabola. To double check, let's put it in my y equals negative 1 over 125, parentheses, x minus 50 squared plus 35. I think I'm going to have to change my window. So let's zoom, fit, and see what it gives me. Here we go. Oh, that doesn't work. My zoom fit didn't work, so let's change my zoom. Let's see here. My x's, they have going from 0 to 80, so we'll go from that, 0 to 80. We probably, here they're counting by 10, 20, so we'll go by tens. And then my y's here, we're going from 0 to 40. And here we're counting by 5 by 5s. And there we go. My graph matches their graph. So let's go ahead and let's double check. Let's trace it. So when we put in a 0, we get 15. When we plug in a 50, let's type in 50, we get my 35. Okay, now let's answer the question. The performer lands in a net 90 feet from the cannon. So we're 90 feet over here. So that's an x of 90 feet. X is 90 feet. What is the height of the net? Remember, my height is my y. So we're trying to find y when x is 90. Well, I can do that by just plugging that in. Plug a 90 in for x. So we'd have y equals negative 1 over 25, 40 squared plus 35. So let's see. Second quit, get back here, negative 1 over 125, is that decimal, times 40 squared plus 35. We get 22.2. So she's 22.2 feet away. Okay, we can also, since we have it in our y equals, in our graph, we can trace it. So when x is 90 feet, oh, it's not going to let us because my zoom doesn't go there. That's what that means, error invalid. Here we can go to, option 2, and that's because my zoom, so let's go back to window, and let's go up to an x of 95 so we can see that far out. That's what I was trying to trace to where my window wasn't. So we'll have to graph. So now we can trace 90 feet, and we do get 22.2. So when I go out 90, 22.2 feet up. Okay, so there we've answered example 1. So now what I want you to do is pause the video and do your turn number 1. Okay, your turn number 1 is very similar to example number 1. So pause the video, do that your turn question. When you're done, resume the video. Okay. All right, so hopefully you finished your turn number 1. Bring that to class with any questions you had or any place you got stuck. We'll discuss it in class. Okay, now let's go on to example 2. Example 2, a meteorologist creates a parabola to predict the temperature tomorrow, where x is the number of hours after midnight. So x here is the number of hours after midnight, and y is the temperature in degrees Celsius. Write a function f that models the temperature over time. What is the coldest temperature? So let's look at our graph here. We have the point 0, 9.6, and then we have the point 40 and 24.0. If you notice, these 2 points right here are where we cross the x-axis. So we have x-intercepts. We have x-intercepts at where? 4 and 24. And we also have a point of 0, 9.6. So we have the x-intercepts and a point. So if we know a point and the x-intercepts, we can use the intercept form. So the intercept form looks like this again, y equals a, x minus p, x minus q, where p and q are the intercepts. So p is 4, q is 24, it doesn't matter which one. So a, x minus 4, x minus 24, y equals. So again, the only thing we're missing is a. We need to find a. Okay. So to find a here, we know a point. We know an x and a y. So let's do the same thing we did on the last problem. Plug in my x and my y to find a. So my y is 9.6, that point it gave me. Sorry, my y is 9.6 equals a. My x is 0, so we'd have 0 minus 4 times 0 minus 24. Okay, let's simplify that. Let's bring it up over here. I'm out of room. So we'd have 9.6 equals a times negative 4 times negative 24. So 4 times 24, I don't know that one, is 96. So we'd have 9.6 equals a times 96. Divide both sides by the 96. So a equals 9.6 divided by 96 is 0.1. 1/10 or 0.1. And since we're dealing with decimals in this problem, I think having 0.1 is okay. Okay, so my function y equals a 0.1 x minus 4 x minus 24. And it says, what is the coldest temperature? Well, the coldest temperature is going to occur here at the minimum. So I need to find my vertex to find that coldest temperature there. So there's a couple different ways of doing it. Now that I have the model, we can see if my calculator can give me one. Let's double check. 0.1 x minus 4 x minus 24. Oh, got to change our window. We don't see into the negatives. So let's go, instead of 0, let's go negative 15 to 15, I think is probably good. There we go. We can trace. Oh, I'm way up here at 54. Let's try, it looks like it's maybe sometime here around 15. Okay, what about 14? Negative 10, 13. So it looks like maybe at 14. Okay, we can find it more exact mathematically, and we'll work through that in class. So we need to come back. Okay, so I want you to see if you can't find where that minimum is. Okay, for that one. Okay, what is the average rate of change in temperature over the interval in which the temperature is decreasing, increasing? Compare the average rates of change. That looks like another good one for in class. So we'll do this one in class also. That's where we'll start class, is finishing up example 2. Okay, so now I want you to pause the video, come in, and do your turn number 2. Okay, it's going to be very similar to what we did for part A of example 2. So pause the video and come back when you're done. Okay. All right, so now we're going to look at some more real world data if we have a data set. When data have equally spaced inputs, you can analyze patterns in the difference of the outputs to determine what type of function can be used to model the data. So for example here, I have this data set, and if you notice, my inputs go up by 1 each time. So my inputs here are equally spaced. It doesn't matter what they go up by as long as it's consistent. They go up by 1s, go up by 2s, as long as they're equally spaced. You go up by 2 each time, so forth and so on. So now we can look at the difference between the outputs, okay, to help us find what type of model, because now we're going to have two different type of models. We had linear ones, and now we're going to introduce quadratic. Okay, so first let's look at how these are spaced. So we have 9 to 4. So I'm going to take the 4. I'm going to look at the difference. 4 minus 9 is negative 5. 1 minus 4 is negative 3. 0 minus 1 is negative 1. 1 minus 0 is 1. 4 minus 1 is 3. 9 minus 4 is 5. So these are what we call the first differences. And if these first differences were all the same, then it would be a linear model, and we do it like we did our linear equations from the beginning of the year. But they're not all the same. All these differences are different. So now let's go ahead and let's take the second difference. Let's subtract again. Negative 3 minus negative 5 is 2. Negative 1 minus negative 3 is 2. 1 minus negative 1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. These are what we call the second differences. And if you notice, these second differences are all the same. So they are the same. So since they are all the same, I know if I was to plot these points, they would fit a quadratic model or a parabola if I was to plot these points. Okay, they would fit that quadratic model. Okay, so we always want to look at those differences to see what type of model. Is it going to be linear? Is it going to be quadratic? It might not be either. Okay, so let's go ahead and let's look at an example here. Example 3, NASA can create weightless environment by flying a plane in a parabolic path. The table shows the height in feet, so here's my height in feet of the plane. Here's my height, t seconds after it starts the flight path. So at time 10 seconds after it starts, that's how high it is. 15 seconds after it starts, that's how high it is. After about 20.8 seconds, passengers begin to experience a weightless environment. Write and evaluate a function to approximate the height at which this occurs. So again, this 20.8 is my t. I'm trying to find h when t is 20.8. So first thing first, it says to write and evaluate a function. So I'm going to look to see, is this going to be a linear function or a quadratic function? Which one? So first let's look, are my inputs, my t equally spaced? 10 to 15 is 5, 5, 5. I'm going up by 5 each time. Yep, so these are equally spaced. So we're good to go on that. So they're equally spaced. So now let's go ahead and let's do some differences. So let's go ahead and easiest way is to just do some subtracting. So these are bigger numbers, so I'm going to use my calculator. 29025 minus 26900. We get 2125. Okay, and let's do the next one. So 3600 minus 29025. We get 1575. So I can tell right now it's not linear because these numbers aren't the same. 31625 minus 30. We get 1025 between these two. Okay, 32100 minus 31625. We get 475 between these two. And 32025 minus 32. It's negative 75. The last one, negative 625. Okay, so the first differences are not all the same, so I know it's not linear. So let's go ahead, let's look at the second differences. So I'm going to take 1575 minus negative 550. Now 1025 minus negative 550. 475. It's looking good. Negative 550. So it looks like my second differences here are all the same. Negative 75 minus negative 550. Okay, we're looking good. So it looks like negative 550. So our second differences. This tells me this is going to be quadratic. Okay, so I have lots of ordered pairs for this. You only need 3. You need 3 ordered pairs. So this is this last type of problem if I'm given 3 points. So I only need 3 points. So I'm just going to go ahead and jot down 3 points. We have 10, 2, 6, 9, 0, 0. Then we have the point 15, 2, 9, 0, 2, 5. And then one other point, 20, 3.600. So I have 3 points. Okay, my goal again is to write a quadratic equation that fits these points. So to do that, I'm going to use standard form. Y equals ax squared plus bx plus c. And I'm going to write 3 equations, one for each of these, using each of these x's and y's. Okay, so I'm going to plug in x for all my x's and a y in for my y for each of these. So I'm going to have 3 different equations. So let's do this first point. So I'm going to plug this as my y, so I'd have 26,900 equals a times x squared. So a times 10 squared, that'd be 100. So if we take a times 100, do you agree that would be 100a? Plus b times my x, which is 10, so that would be 10b plus c. So there's one equation. This equation came from using that point. Now I'm going to do the same thing using my second point. So my y is 2,925. Now I plug my 15 in for my x. So I take 15 squared, which is 225. I did that on my calculator, 225a, plus now b times x. My x is 15, so 15b plus c. Okay, so that one came from my second equation, my second point, and now my third equation will come from this one. So we'll have 3600 equals, now we put in the 20, so we'll go 20 squared, which is 400a plus 20b. Again, I'm just putting a 20 in there for x plus c. So now I have a system of 3 equations and 3 unknowns. Now I just need to solve it, solve this system. So again, how do we solve systems? What do? We add equations and get rid of variables. Well, if you notice, my c is just a c on all of them. So I'm going to take this first one times -1 and add them to both of these. So that would be -26,900, -100a, minus 10b, minus c, and I'm going to add it to the second equation. 29025, 225a, plus 15b, plus c. Okay, so now when we add it, so -26,900 plus 29025, we get 2125. 225 minus, oh, what am I doing that for? That's 125a plus 5b. Okay, so there's one equation. Now let's do the same thing with the other one. We're going to take again that -26,900 equals -100a minus 10b minus c. We're going to add that to 3600. Add them up. 600. Oh, minus. So give me 300a plus 10b and no c. Okay, so now I have 2 equations here. Let's see, I can get rid of b's if I multiply this by -2 and add it to that. So 25 times -2 is -4250. 125 times -2 gives me -250a minus 10b. Add those two. Minus 42. So -550, 300 minus 250 gives me 50a. And then my b's are gone there. Divide both sides by the 50. A is -11. So we found A for my equation. So now we have this piece. So now I just need to plug this A back into one of these to find B. So here we can go in this one, 125 times -11 plus 5B. 125 times -11. So we have 2125 equals -1375. Plus 5b. So if I add the 1375 to the other side, 2125 plus 1375, and then divide it by the 5, b is 700. So we have b, and now we just need to find c. So again, to find c, I'm just going to plug these back up into one of these 3. So let's see, I don't know, the first one's good as any, doesn't really much matter. 100 times a, which is -11, plus 10 times b, which is 700, oop, I'm out of room, plus c. Okay, so we have 100 times negative 11, that's negative 1100. Mrs. Neal, come on. Negative 1100 plus 7,000, I believe, plus c. 10 times 700, 7,000. Negative 11, 5,900. Subtract that to the other side, 26,900 minus. So my c is 21,000. Okay, so then my equation is y equals, we know my a is negative 11 x squared, plus my b there is 700 x, plus my c is, so there's my equation. The real test is if I was to graph this, okay, would these points work? Let's see, 10, it worked. What about 15? Yep, 20? Yepers, we got it. Okay. Alrighty, so again, this is the most complicated of the quadratic functions, okay? You will not be expected to do a lot of these, but you will need to know the process. Again, it's just solving a system of equations, really, writing your system and solving it. These numbers weren't the prettiest, but they weren't that bad either. They were just big. Okay. Now, real life data that shows a quadratic relationship usually do not have constant second differences because the data are not exactly quadratic. So for data that's not exactly quadratic, we could use a calculator and a quadratic regression to model relationships that are approximately quadratic, which means, again, they'll have that correlation coefficient. So we work through this process the exact same as we did the linear ones. Remember, we did stat, and then we inputted our data, so we went to edit, and then we inputted our data, and then once we were done doing that, we could do stat calculate, but instead of doing a linear regression to get a line, we can do a quadratic regression, option 5. So you work through the exact same process to get that quadratic equation. So I'm going to go ahead and do this first one. So the table shows the fuel efficiencies of a vehicle at different speeds. So depending on how fast you go, the type of gas mileage you get. Okay, so let's go ahead and let's type these in. So when I get into stat and edit, and we plug them in, 20, 24, 30, 36, 40, 45, 50, 56, 60, and 70. And now we plug 14.5, 17.5, 21.2, 23.7, 25.2, 25.8, 24, 19.5. Again, we can graph this data. I'm going to delete my y equals, go up to plot 1, turn plot 1 on, change my zoom button to zoom stat, so it fits my statistics in it, and there's my data. As you can tell, it looks parabolic. It looks quadratic. Okay, so then now we can actually get that quadratic equation using our calculator. We go to stat, over to calc, and then we go to quadratic regression, option 5. Again, it looks the same, except instead of saying lin regression up there, it says quadratic. We use list 1, list 2. Again, I want to store this regression in my y1. So I'm going to hit vars, right here, vars, and then arrow over to y vars, function, y1. So I'm telling my calculator I want it to put it in y1, arrow down to calculate. So here's my equation. They found my a, my b, and my c for my standard form. So this model, this equation is y equals my a, which is negative 0.014 x to the second, plus my b, which is 1.366 x, plus my c, which is a negative 7.144. Kind of went 3 decimal places. Okay, and again, so there's my equation. Again, we have my ax squared plus bx plus c. Okay, and my R2 value, there's my correlation coefficient. In quadratics, it's the R2 and not just the R. Okay, and again, it's 0.999, which again, we want that close to 1 or negative 1. So this fits my data pretty good. And since I had it put it in my Y1, you can see how well that fits my data. Okay. So now use the model to approximate the optimal driving speed. I want you to try to use this model and find out what's the optimal driving speed, meaning what speed should I have to get the best gas mileage. Again, remember your X is your speed in miles per hour, your Y is your gas mileage in miles per gallon. Okay, and then I want you to go ahead and do your turn number 4, come back to class with questions ready to discuss.